Okay, well, let's go ahead and get started. Welcome to If You Can't Open It, You Don't Own It. Does anybody know where that comes from? Do we have any hardware engineers in here? So this actually comes from, it's not original to me, it comes from hardware hackers. And they always say that if you can't get inside the box, you can't own the hardware. So that's where the title of this comes from. Has everybody heard about Dick Cheney's pacemaker? So I was reading an article, this is after he left the government. He was being fitted for pacemakers. He had all sorts of heart problems, and he, going through the article, it just was telling about his history of heart problems and why he was having a pacemaker. And then there was this throwaway line where it said, oh, and the Secret Service made him turn off the Wi-Fi. And I was like, yeah, I mean, why do you have a Wi-Fi transmitter and a pacemaker anyway? Well, it's mainly for diagnostics, but what they didn't understand is that when you put Wi-Fi in a pacemaker, now all of a sudden somebody from the outside can get into it. And they found out later that those have actually been hacked, along with, I have a friend who's got he's diabetic, so he's got an insulin pump. And a researcher named Barnaby Jack managed to penetrate into an insulin pump and get it to dispense all 300 units of its insulin because it had Wi-Fi in it too. So we're beginning to put in all sorts of things into hardware and into our systems that allow people to get to it from the outside, which are things we really don't want to put in. And this is where we get into the dark art of hardware hacking. So let's start with Shadowhammer. So Shadowhammer is only, this was last year, and we're not entirely sure at this point who got into it. You hear people talk about attribution all the time, but attribution is a little bit hard to figure out, mainly because it could be this country making that country look like they were the ones that did it, and they put just enough into it to divert attention away from them. But somebody got into ASUS's, basically into their software, added malware into the software before it was compiled, before it was signed in their CPU servers, and when they sent this out, it went out to about 500,000 computers. So this was in the firmware. This is the very lowest level software you can get. And what was interesting about this, though, was they were only looking for 600 computers based on a MAC address. Now, if you've ever tried to do something like that, just getting the MAC address of very specific computers can be very difficult to do, which means this is probably a nation-state level attack. But what it does is it takes us into a conversation about roots of trust. So has anybody heard of roots of trust? Okay, Herb has heard of roots of trust. So roots of trust have to do with our ability to build software and hardware systems up from the bottom, and that we have this implied trust between the level we're at and the levels below it. So we inherently trust the operating system because that's where our software runs. The software system, the operating system trusts the hardware. So this is a pretty good definition from NIST about what hardware roots of trust are, and what it is it's about having that as you go down into the levels, it's harder to hack. Therefore, you should be able to have more trust in the lowest levels. So for us, we trust the hardware because that's the hardest to hack. But as you begin moving up, it becomes progressively easier. So this is the trust landscape that we work with today. So we have a scheme as we begin to go down into the different layers. They get farther and farther away from people being able to access them, but that trust is organic. So in the case of Shadowhammer, it invaded the very lowest level of trust, which was down where the firmware was. So that's as low as you can get, which means you're now in a position to compromise everything going upwards. So one of the reasons why we inherently trust the hardware is because it is so hard to hack. It's the farthest away from people. We usually, when you have an IoT device, for example, you're not really talking directly to the hardware. You may be talking in through Wi-Fi, but you're going to be dealing with an operating system. And actually getting down to the hardware can be much more difficult. But what happens when we break the trust? This is an example, and this was not done by hackers. This was actually done by researchers. But here we have this comes from a car, and in this case we have a bus which is connecting all of the parts which are there to get the car from point A to point B. So this is about driving being able to drive the car. But in this case, they began to mix trust layers. So we have an area where we have a higher level of required trust, which is getting the car from point A to point B. That's the part that drives the car. And then we have another part that is a lower level of trust, which is the infotainment system. Except when they did their design, they actually had the infotainment system share that CAN bus in the middle. So what they did was they went into an area where they had a vulnerability in their infotainment system that allowed them to jump off into the hardware architecture where they've got these two buses mixing together. And then that allowed them to get into the power systems of being able to drive the vehicle. So when you're designing your systems, and specifically when you're looking at hardware systems, you have to make sure that as you build those roots, those trusts, that you're thinking about what are the different trust levels that I have. Do I have a low trust system that's intermingling with a system that requires high trust? And oddly enough, in most systems, I don't know, is anybody here in the automotive industry? I know we have a few here, sort of. One of the things you find is that we spend more time and we have more code. For example, on the Boeing 777, there's more code written for the infotainment system than there is code actually written for the computer systems that fly the aircraft from point A to point B. So in this case, they have mixed trusts, which allowed them to be able to jump from one area to another. So our software implicitly trusts a lot of things. Our kernel, the libraries, the hardware we're working on, the firmware. And we also implicitly trust the security system. So we have permissions, ACLs, we have the communications pathways, our update system. So we have all of these trust relationships that we have to manage. But the problem is when those trusts get broken, we now have to ask, what can we trust? So we can't trust the hardware because we don't own the hardware. We can't trust the kernel because we don't have any control over it. We don't trust the constraints in our system simply because those constraints can be bypassed. We don't always either write our libraries or have them secured, so it's easy to get past those. The update system, as we just saw with Shadowhammer, can be gotten past. So we have all of these things that we implicitly trust, but the reality is we can't. So the question becomes, what can we trust? Anybody? So you can trust what you control. You can trust the code you write and the code you compile. You can trust the libraries you use, and this includes third-party libraries. The question is, are those libraries such that you do have the ability to trust them? You can trust who and what you connect with because you choose who you connect with and how you have communications with them. And you can trust what you have in memory, but that also means you have a responsibility to manage all of these different elements. So what you compile, again, don't mix trust levels. When you're building your system, understand that you're going to have to make an evaluation in the architecture of what requires a high level of trust, simply because this is something that does something vital versus the things that you tend to do that have a low level of trust. I once had a case where our printer got hacked. My wife went to a university and she was doing research and someone had run a water holding attack on it, and they had managed to replace the firmware on the printer. And after about 2 hours of rooting around where I could begin seeing that there was traffic coming off of this printer going to strange IP addresses, I finally figured out that they had replaced the firmware, but they hadn't done it exactly right. And if you hadn't tried to print, you wouldn't have known that the printer actually didn't work. So this is a case where you have a high level of trust, which is your PC and your network. You have something that's basically a low level of trust, which should just be your printer. I mean, that's supposed to take information to it and then spit out a page. It's not actually supposed to do anything. But we have done things with printers where we now allow printers to act as servers. We now allow printers, some of them can act as DNS relays. We have all sorts of things, email relays. We've put things into printers that allow people to use those, that we can no longer think of those as basically a low trust piece in your high trust environment. So one of the things that, how many people sign their code before they put it out? So if you work in the hardware world, you do this for sure. But then when you start it up, do you go verify the signature? Yeah, well, I've seen people shake their heads. No, we sign our code because it makes it feel better that we're signing the code so we know it's on the box, but what happens if I replace it once it's on the box? If you don't check the signature to make sure that that actually is the code that you put down, then all of a sudden you no longer have a trust that that code is actually what you're running is what you thought you were running. The other thing I always recommend, and again, these are recommendations, is encrypt your traffic even if you're going over Wi-Fi. So WPA's been compromised, WPA2's been compromised, there are all sorts of attacks against it. You are in control of your transport layer. If you're relying specifically on somebody else to encrypt it, you may find out that that was a misplaced trust. So you have a broken trust relationship there at a time when you really can't afford to have it broken. The libraries you use. This is something that's sort of controversial. For the record, I use third-party libraries all the time, but a lot of times we'll go grab a third-party library because it solves a problem. It's the fastest way for us to be able to get our software out the door. We drop it in, but we don't actually verify whether or not that third-party library is doing things we don't expect. So in the case of third-party libraries, if you didn't write it, if you haven't code reviewed it to the point where you know exactly how this library is working, what it's doing, or you don't know and more importantly trust the person who did write that library, then you're taking a risk because that library now is behind whatever protections you have. So that library now becomes your liability. So no matter what functionality it gives you, you have to make sure that what you're using is actually not only going to do what it's supposed to do, but it's not doing other things that you don't know. And it doesn't have to be malicious. We'll talk about a case this afternoon about a case where someone did put malicious code into a library, and it was a widely used library, but it could just be doing something incorrectly. If it's got vulnerabilities in its code, that means that that code can be used in order to penetrate your system, so it becomes the liability behind your defenses. So who and what you connect with. We have a tendency, for example, if you use IPC mechanisms, you have multiple processes. Very few people have a single monolithic process. You're either going to do microservices or you're doing multiple processes, and those services and processes all have to communicate with each other. But if you don't validate and verify who that process is, then you may very well find out that someone like me comes and replaces that binary with my binary, and now you're talking to someone you don't expect. And this has happened. It's very easy, for example, on an installer not to put the correct permissions on a service so that now someone can come and just drop another binary in place, and now they're running their binaries as your service with system access. So in this case, force the authentication. Don't assume that just because somebody can talk to you on your IPC connection that it's actually the person you think it is. And then the last one is what you hold in memory. I have seen so many cases in the last 30 years where people will put shared secrets. And anybody done that? I mean, I've worked on systems where we've had that, where you put a shared secret in there, and some people are sort of sheepishly shaking, nodding their heads saying, yeah, we did that. The problem with a shared secret is it's not a secret. So if I have your binary, I can run a string, a little application that just yanks out all the strings and just prints them out for me. And now I can just begin trying one after another to see whether your shared secret is really a secret. So if you're going to, and I highly suggest that you do this, but if you're going to have keys where you have to authenticate who you're talking to, those really need to go into some sort of a secure store, what's called a trusted platform module, where you want those keys locked up not in your binaries, not hard-coded in your binaries. I know it's easy to do, especially if you're talking about something like I had one time where we just wanted to talk to the HTTP server, but we wanted to make sure that it was only our equipment that was talking to HTTP. So they decided, well, we'll put in a shared secret that goes up, it checks it, it comes down. Well, what if they find it? Well, we'll put a timestamp on it, and it just becomes one of these. Use SSL. That's what it's there for. There's no reason to roll your own crypto. That's one of the first rules of encryption and security is don't roll your own. Use what what people have developed over years, because if you roll your own, you're probably going to get it wrong. And then here's the one that sort of catches everybody. So I bring in my encrypted key, I decrypt it, I use it, I clear the memory. And I think I'm good because as we've talked about Meltdown and Spectre and how they can go after memory based on timing attacks, the problem is that the compiler will look at that and it'll say, okay, you brought it in, you used it, you cleared it, but then you didn't do anything else with it, which means there's no side effects, which means really that clear has nothing to do, so I can optimize that away. So if you have code where you are bringing something in, you'll want to, that's critical, like a key, you'll want to have that key, use it, and then get rid of it. But if you're not clearing it correctly, that key's actually still going to be in memory. And you're vulnerable to not just side channel attacks, but use after free attacks. So the takeaways. Don't mix trust levels. It may be convenient, and I can understand from a hardware perspective why you would have a single CAN bus within a vehicle or a single bus within an aircraft, but when you mix those trust environments together, it makes it easier for somebody to go in through an untrusted system and going through and be able to get to your trust area. That's why if you've ever worked in a cleared environment, you'll have one PC for untrusted work, so that's what goes to the internet. You'll have another PC that actually goes into the trusted network, and they're physically separate. So when you design your systems, whether it's hardware or software, make sure that your trust zones are separate. Validate your binaries. Too many times people will sign the binaries. In fact, I had somebody ask me the other day is whether it was better to have a signed binary from an untrusted source or that you're getting the binary from a source you trust. And the reality is they're both equally insecure. You can't guarantee the trust level of the person you're getting it from, and if it's signed by an untrusted source, that's not a signed source, that's nothing. So make sure that if you're going to, especially where you're transmitting software, sign your binaries, and when the binaries come up, when they're run, go and check to make sure that that binary hasn't been replaced. And then manage your own ecosystem. It's really easy to get into the habit of thinking we're going to let the ACLs or the security of the system manage itself. But once they've gotten past that one layer of security, if you have nothing beyond that, you're completely exposed. That's why when you're talking about building something where you have to worry about the security, and that's almost all of us, we talk about defense in depth. Where we learned this the hard way, so we have a perimeter of the hardware perimeter we call firewalls. But once somebody gets past that, everything else is pretty much open. Now you have to begin to think about a layered defense where it becomes a bigger problem, where each layer has to be yet another attack that they have to launch in order to be able to get to to the golden nugget, the thing that it is that you're protecting. So ultimately, in the end, there's nothing you can really trust that you don't have control over. So the only things you really can trust are the things that you actually physically control. And we'll talk about third-party libraries here in just a bit. So I loved this quote. This actually came from an article, which is the part we'll talk about here in a few minutes. But hardware hacking, and this is why hardware hacking is so much fun, is just because it is it requires so many different disciplines, both software and hardware and physics, and a lot of ingenuity. And this is one of my favorite hacks. This is from a security researcher. And he was going through and he was wondering whether or not he had heard rumors that there was these extra commands on a processor that you could somehow activate. So he's going through this patent, and it says, additionally, accessing some of the internal control registers can enable the users to bypass security mechanisms, i.e. allowing ring 0 access at ring 3. Which is bad. That's like a normal user being able to get root access. In addition, the control registers may reveal information that the processor designers wish to keep proprietary. Yeah, for the obvious reason that you don't want to teach people on your processor how to get ring 0 access as a normal user. For these reasons, the various x86 processor manufacturers have not publicly documented any description of the address or function of some control MSRs. So there we have a problem. Why do you even have these in there? Has anybody ever put a backdoor in their software that only they knew? Maybe it was an easy password or it was a command line utility. Yeah, I've got some people sort of sheepishly nodding their heads. It looks like, no, I never did anything like that, but their eyes are saying something different. And what he was going after was this C2 x86 CPU. And when he talked about it, he was sort of listing out the things that it was used in. He goes, yeah, and it's control systems and medical and this and that. And I was like, wait a minute, medical? Which pieces of medical equipment did they put this in that it can now be hacked? But what he did was really ingenious. So ring three is the application area. And then as we got to ring 0, and then we decided, well, we needed something a little more than ring 0. So now you have the hypervisor, the system management code, and a bunch of other things that are actually sort of deeper in that have increasingly more capabilities. So what he did was, so if you're not a hardware engineer, MSRs are model-specific registers. And so these are 64-bit registers that are not defined by name anywhere, but you'll use a couple of commands to be able to access them. So so the question became, well, how do you know if these even exist? So what he wound up doing was he wound up going through all of them, and he identified 1,300 that exist. And the only way you knew they existed is that you didn't have a kernel panic or it didn't crash the system. So it obviously did something other than kill the system. So then he used a really clever timing attack to do this. And what he basically said is, well, if it's the same command, the time to run that command should be the same. But if it's a different command than the one I just tried, then those MSRs should actually have different timings. So this is a case of a timing attack where I'm basically going to go try all of these and I'm going to look at the timings. And if they all have the same timing, I know they're probably the same thing. But if they have different timings, I know that's one that's called out that I want to go and investigate. So he did this timing attack, which timing is just a side channel. And he identified 43 out of the 1,300. So he's cut his work quite a bit. The problem is that when you take the number of bits and you do the math, and I have no idea what 10 to the 36th is, it's a very big number, which basically means we're going to take the rest of his life to do it. So if we have a system that we want to check and it's got all these combinations, what do? Right, scale it up. So what he did was he took a lot of these, put them together into a rig, and he created a system called SandSifter that scanned each one of them, and he finally found an MSR 1107 bit 0 turned on God mode, which gave him complete access to the processor, which, depending on where this is now a horrifying prospect. So this is the NIST definition. They actually had that as cryptographic systems, what applies to anything. I am going to start with a cryptographic example. This is an RSA timing power attack where what we're doing is this, what you see down at the bottom is the Spectre analyzer output for it, that where you see those spikes, you can actually see the operation, the algorithm in operation, and you can tell whether it's an even or an odd. And it depends, because of the formula above there tells you that when you're talking about power, the more circuits, the more power it should take, the longer it should take, versus down at the bottom. So here you can tell the evens and the odds just by looking at the Spectrum analyzer output. We also have differential fault analysis. So what we're going to do is we're going to go and we're just going to inject faults into the system. We want to see how the system reacts when we put a fault in it. Then you put another fault in it, and you look each time to see how it reacts, and you measure the outcome. So has anybody heard of Tempest? Okay, so hardware engineers will know about Tempest because this is about the emissions that that whatever piece of equipment you're putting out, these are going to be the emissions, whether it's going to be RF emissions or a thermal signature. So what's to the right there is just a thermal signature of a board, where you see in the middle, there's that very bright spot. This is actually coming from underneath the chip for some reason. I don't know the exact backstory for it. This is not a BGA, is one where all the pins are sort of in the middle, and they're the balls of solder, and then you put them down, run them through a reflow oven, and that's how it gets put into the board. These are actually soldered on the outside. So in this case, you either have something under there or it's under a heavy load, but it tells you something about what that processor is doing. This is another example of what's known as a sideband analysis, where you're looking at the emissions from a monitor. So the center frequency is the bright line in the middle, but if you look down each one of these for different bit patterns, you get slightly different striations coming on the display. So now you can begin to tell which one of these things, what is being displayed on the screen. So it used to be, because the monitors leaked so badly, that you could actually tell from quite a ways away what was on that screen. So let's talk about software. So cache bleed was an SSL. This is not Heartbleed. This is cache bleed, but it was an SSL attack, and then everybody knows about Meltdown and Spectre. Okay, we're not going to talk about those today because everybody knows. Concurrency, Dirty Cow. If you were here last year and went to my talk, or in Seattle, Dirty Cow was actually a concurrency bug that had been in Linux for 9 years. And what it allowed you to do was be able to go and by doing something their copy on write, which allowed you to play with the timing, what it wound up doing is it wound up allowing you to write to files you didn't have permissions to write. For memory, use after free, where we can force a memory overflow, or we can make use of memory even after it's supposedly been released back to the system, allows you to alter the control flow. So there's a use after free is pretty good at is a very hard bug to find, but it is one where you can use it to alter control flow, because you might have two pointers. You've created this memory, you freed it, but you didn't change the pointer back. You didn't null it. And then somebody creates memory again, but it's at the exact same spot where the last piece of memory was. And then now all of a sudden you have two pointers going to the same memory, except only one of you's actually using that memory correctly. So we talked about holding keys in memory after use. If you're going to bring in keys, or if you're using something that's sensitive, bring it in, use it, and then get rid of it. Because the longer it stays in memory, the longer it can be used. And then data type conversions for us can produce undefined behavior and create vulnerabilities in our code. So Wi-Fi. This goes back to why I was saying that you want to control your own ecosystem. If you are sending information off of your box, don't just trust that it's going over Wi-Fi and say, okay, Wi-Fi is good. Certainly not over a network. This is why you do encryption when you're talking to people on the internet. So if you have one system on one side of the world and another system on the other side, you wouldn't even think twice about encrypting that traffic. But when you realize that when we're inside the wire, and that's no more trusted than what's outside the wire, you should be encrypting your traffic as well. And we already talked about WPA and WPA2. Network timing is also sort of a different way. This is something that's sort of been on the rise, is people are looking at side channel attacks, looking at how your network traffic moves over time. So Netflix has and I don't have Netflix, so I don't know exactly what it is they're transmitting, but you apparently have the ability of deciding where you're wanting to say, I like this one or I didn't like that one. What you can do is decode those packets or look at the timing that come across it. The packets are encrypted, but you can look at the timing and tell what somebody is doing, what choice they made. So network traffic analysis has become, in this case, where you want to make sure that there isn't any data that any side channels coming out of your network traffic, by making your network traffic look as innocuous as you possibly can, so that there's no timings to it. This is the one where I see a lot of problems. We put account information in our logs and our error messages. We put in paths and locations to sensitive information. We have function names. Almost all of us have debug code where you turn up the debugger and suddenly we're beginning to see the function names appear. The problem is that allows people to go back and trace your program execution flow just by looking at the logs. How many people actually secure their logs in their systems? Yeah, one person? 2 people. most of us don't, because we don't consider that to really be valuable information. But whenever I penetrate a system, that's actually the first thing I go look for, is I want all the logs. If you have a config file that's not secured in any way, it's not encrypted. I've seen config files where they base64 encoded the data because they thought, oh, well, they're not going to be able to read it. Oh, sure, because you can just reverse it back out. It's not that hard at all. It does not give you, we'll talk about, when we talk about security through obscurity is not security. It never has been. In fact, if anything, it gives us a false sense of security. So censor what you're putting in your log messages and what you're putting in your error messages. Licensing can also become problematic because some licenses require you to redistribute source code. So if you make changes to something in their library, or you use their library and you make changes in your code, you may be legally obligated to go and produce the source code that is using it. And that becomes a significant problem, because not only is it a problem that I know you're using the library, for example, I know you're using SSL. So since the source code of SSL is freely available, I now can go and take the source code for SSL, you tell me in your banner that you're using SSL, whatever. Well, now I know whatever vulnerabilities are in there. And it's even worse if you're using an SSL version that's out of date. If your SSL version is 3 years old, you have a lot of vulnerabilities in there. And one of the first things I'll do is when I find out that you're doing that, I'm going to go look at the CVE database, find out what bugs have been logged against it. Usually they'll tell me how to exploit it, and then that's the way into your system. So be careful when now, normally you have no choice, and it's only fair. If you're going to use somebody else's library, you should let people know that you're using their library if that's what they want. That's part of the deal. But you understand that you're taking a risk. You're leaking information, so it becomes a side channel. This turned off. So side channel attacks are anything that you leak. So when you're going through and you're building your system, whether it is where you're trying to, you're putting it into your logs or your config file, go and ask yourself, is there a way that this information becomes valuable to somebody? And specifically, the things that are easier to get to. If you're not securing your logs, if you're not securing your config file, I would. There's nobody needs to see those particular pieces, those artifacts of your system except for you. And then the other thing is, don't rely on first-line crypto. Everybody was saying, oh, WPA is fine, right up until it's broken. The problem is there's a long lag time between the time that it's broken and the time that it's generally known. And then you don't control. You may be going over a Wi-Fi network that you don't have any control over, so you don't get to control their particular setup. So DigiNotar, this was a Dutch certificate authority. And what happened here was they had this really incredibly elaborate system. They had done everything right. They had perimeter security. They had all sorts of access controls. They had this room, if you've ever seen Mission Impossible, where he's hanging down from the ceiling and he's on the computer suspended in midair. They had that kind of control. You had to have a palm print and there had to be a card in the machine. And the problem was somebody decided to leave the card in the machine out of convenience, which was sort of their last. That was sort of they were really practicing defense in depth, except that they managed to violate their very last stage, which was the one that you couldn't undo. That was the one where if that card's not there, it doesn't matter how far someone has penetrated into their system, they couldn't do anything. But they left the card in, which was the last line of defense that they had. So what happened was they got in and they created, this turned out to be a nation state attack. They got in and created a bunch of certificates. This was mainly having to do with Google, so that you could, and you have to have control over DNS. So you'd use a DNS poisoning attack, so that allows you to go in and change DNS to reroute it to your IP address. You've created the certificates, and the only way that this was exposed was that Google understood, the Google browser understood where its certificates came from. And when Google saw these are not our certificates, they started rejecting it. And so that's the only way we knew. In this case, the company wound up failing mainly because they didn't want to admit that this had happened, and they waited a very long time to let people know. The Dutch government took it over and then ultimately dissolved it. But this is a case of where physical security, where when you violate that last line of security, you have to assume that someone has already gotten through the other ones. So let's talk about physical access. For hardware, there is remote and local. So if I can talk to you, I now have the ability to touch you at a distance. Local is debugging access. If you do any hardware, you'll know what a JTAG port is. There is physically invasive, where you're injecting faults, and then there's destructive, where we're literally going and taking the thing apart. So this is a case of when we're reverse engineering something. X-ray computed tomography, that's on the right. That's where you take an X-ray that's hooked up to a computer and it goes and evaluates, and it can tell you exactly how that circuit operates. Decapsulation is where we literally just whack the top of the chip off, and now we can see all the circuitry inside. So for reverse engineering, there are a couple of really interesting tools. There's Bus Pirate, which is a signal tester to see what kind of traffic is coming out of your hardware. We have digital logical analyzers, so if you want to analyze the protocol for something like SPI or I2C, what will happen in hardware is that when they go out, they'll take the JTAG ports off, and they'll take the serial ports off because they don't want you to be able to watch the boot cycle. There's also a single wire debug, which puts data out across that pin. They'll take all those off. One of the first things you do is you go and you put all that back on, and then you can reverse engineer software. So for reverse engineering here, for software, we have things like websites. If you go to anybody's website, especially in their technical support forums, you will find tons of information about how the software operates, more than they probably need to give in order for the person to be able to fix whatever problem they have. Again, our log files. If you do nothing more than secure your log files, you're way ahead of the game, and that's just making it so that somebody from the outside can't get to it. If they've got root access on the box, there's not a lot you can do after that. You can encrypt, but nobody's going to encrypt their log files. It winds up carrying too much overhead. System artifacts like your config files. The Windows registry is a huge trove. I know it's convenient. I know we like to use it. I know it's fashionable, but it's really easy to find out lots of things. Plus, I can go in and change things in the Windows registry, because unless that particular key is read-only, I can go in and change your system without you really knowing it, because you're operating based on what's in the registry. Binaries. I have shipped debug code by accident. Make sure you strip out the singles. Don't bake your crypto keys in. There are no shared secrets. There's just secrets everybody knows. Some of these things require a lot of assembly language, but a lot of C++ engineers are very good at. Most hackers are very good at assembly language as well. Here are some tools. Later in the week, Galsban's going to be reconstruct C++ virtual tables with her system, so that's right here at CppCon. So that's another thing you can use, is to go and take the binaries and reconstitute the source code. Our IPC interfaces, those are huge, huge places where people can go in and find, be able to fuzz your system, look at the reactions. So encrypt that traffic and authenticate. Make sure you know who you're talking to. That's also a really good DDoS path for people, is if they know they can crash your system, your I2C interfaces or your IPC interfaces are very good for that. The other thing is your protocols. If you know the protocol that somebody's using, then that makes it much easier for you to operate within the system in such a way that they don't know you're doing it. It's easier to get past repudiation, where you can't tell, somebody did something because it may show up on a log. So treat your protocols like they're intellectual property, because they are. That's the life's blood of your system and how they interact. Command line interfaces. Anybody here in hardware who's ever put a CLI out with their system? Hardware engineers do this all the time. It's so easy. It's a little binary. The first thing you do, you run the binary. It gives you a nice help screen. It tells you all the things that it can do, and here's the command language. And so now you have, and what the system does is it implicitly trusts that anything coming across that IPC interface is actually from a trusted source, and it's not because you didn't authenticate it and you don't know who ran it. So the takeaways. Focus, if you're worried about it, and you should be, but when you're thinking about the security of your system, think about the things that people can do from the outside. If I've got physical access, don't trust the fact that you're running inside of a secure environment, because there are no secure environments anymore. You have to assume that if somebody gets inside, that they're going to be able to do the same things to your system that you will be able to do to your system, except they won't be doing them for nice reasons. Okay, so here is, now there's a lot of controversy about this one. Has anybody heard of the Supermicro hack? Yeah, a couple of people. So the controversy here is that Bloomberg reported a story where a nation state had managed to put a very small chip onto the Supermicro's boards. And Bloomberg stood behind them. These are boards that are used everywhere. Amazon uses them, a bunch of Apple, I think, had a bunch of them. And every company that had these that were using this categorically denied that this had ever happened on their boards, which is kind of strange because when you're talking about publicly traded companies, they usually tend to want to leave a little bit of wiggle room. And it's, well, we think it was, the story was mischaracterized or it was inaccurate or something like that. No, they came out and straight up denied it, which is a pretty risky thing if there's even a chance that this happened. So, did it happen? Well, we don't really know. But this is a really cool thing if they did actually manage to do this, because this really is like watching a unicorn jump over a rainbow. Because what you have to do when you're talking about a really good nation-state hack onto a supply chain is really difficult to do. So you can interdict. So there are times when you intercept the hardware and you modify it. If anybody has ever done any hardware engineering, actually modifying a board is actually pretty hard once it's already been laid down, everything is on there. It's actually fairly hard to do that without being noticed. There is seeding, which is you've inserted this, you've gotten into the manufacturing process where you're now actually changing it just before it goes out. So if you were to be able to get in and change the design, you'd have an engineer that's working there, they're working with you. This is equally as hard. This requires a lot of work. So this is like nation-state level testing. So what they do in order to try and deal with this particular private problem. One is random testing, on-site inspections, monitoring for behavior. You put it into a test environment. You look at the emissions. You want to see what it's doing. The problem with these is that random testing, I don't have to get to every unit. If I do 5% in a million, that's a really low number. Your odds of catching me are about 5%, unless I'm a little smarter than that. On-site inspections, if they're smart enough to do this, they're probably smart enough to get away with it. And then monitoring anomalous behavior, that works to a point, but you have to know what to look for and what is and is not suspicious. And if anybody has ever done any sort of intrusion detection, it's one thing to say, okay, I know what real traffic looks like, therefore anything that doesn't fit the pattern must be somebody in my environment doing something they're not supposed to. But the problem is figuring out what real traffic looks like. It's a lot harder than we think. So again, back to open source. Have you even looked at the source code of the open source libraries that you're using? Do you trust the authors? Sometimes that trust will get broken where ownership changes. With closed source, you have to ask about, is the company reputable? How well have they gone in and tested their security and made sure that their environment is secure? Because remember, their security vulnerabilities are going to become yours. So this is one, and I have personal experience with this one. So in this case, you have a long-running library that lots and lots of people use, millions of downloads in a week. And the maintainer gets tired of maintaining it. So they transfer it. Somebody raises their hand and says, I'll take it. Does not check to see who this person is. Doesn't even know them. Couldn't pick them out of a lineup if their life depended on it. And they just transferred it, and then they didn't say anything to anybody. This person on this Write9 control went in, and he didn't modify the library he just took ownership of. He modified a library it was using. So if you were expecting to find it in this library, you wouldn't see it. It was actually in a downstream library, and one he added sort of innocuously. There was no way, there's nothing that would have tipped you off. But what it was doing Bitcoin mining, and if you had a CoPay wallet anywhere in your system, it would recognize it and go and start mining all the Bitcoin out of your wallet. So this is one of those examples of why you have to sort of become responsible for the third-party libraries and making sure that, and it's not just at a point in time that it's been code reviewed. You have to manage that over time, because you may have these libraries in there in your systems for decades. So just remember that third-party libraries may be free, but they're not. You do have to make sure that those are they're doing what they're supposed to do, but also doing things they're not supposed to do. Even if it's not malicious, it's something that they can do accidentally, which puts a vulnerability into your system. Code reviewing them. Most people don't. Even with Heartbleed, if I had gone through there and looked at that, or Dirty Cow, and I'd looked in the Linux kernel at that piece of code, I probably couldn't have told you that those vulnerabilities were there. It's very, very difficult to find. These were very subtle bugs that somebody did find. Obviously, they took advantage of them. One of the things I think as an industry we need to do is start practicing tough love. If you're a library author and you get a security vulnerability, and you think, well, I'll fix it next month, and the next month, well, I'm going on vacation, I'll fix it the month after. At some point in time, if you're going to produce a library that people are relying on, you have an obligation to fix those types of vulnerabilities, and then we as a community have an obligation to make sure that they get fixed, even if we have to out them to get it done. The other thing you can do is test your third-party libraries. This is I've done this a couple of times, but it's sort of a strange way of going about it, in that you go put it into a test rig and you run it through its paces. What's it doing on the hard drive? Who's it talking to? What ports are opening? You go and look and see how this operates. It doesn't always help if there's a beaconing system in there, because a beaconing system will just wait until it gets a command before it does anything. So if you've got a fairly large library, it's very easy to hide a beacon deep in the core, in the library itself that won't necessarily go off when you think it's when you're testing it. So the thing I always tell people is you're only as strong as your weakest third-party library. Those third-party libraries are becoming the Achilles heel of a lot of pieces of software. So one of the things you can do is go look at things like Black Duck and White Source, these are specifically designed these are companies that will go out, look at the third-party libraries. They'll go check the common vulnerabilities databases to find out what defects are logged against it. They will begin to, and they give you some visibility into I know we use libcurl a lot in softwares that I have used. And yet, if you go back and look in their history, they have had a lot of very serious bugs that if you haven't been updating your library and you don't know that, those are in there in your system as if you wrote the bug. So let's talk about C++20 real quick. Where are we? 10 minutes, okay. Here are the things that we're beginning to do in C++20 that will help you write more secure code. So concepts have been called a type system for the type system, but if you followed the standards, they're based on the concept TS, and what it allows you to do is this. If you wanted to know in the top code whether or not the top block is this sortable, you would have to do something like a static assert. The problem is that's a runtime check. That's not something you can really check at compile time. You can do it slightly bit differently, where you're sort of almost the block below is creating sort of a concept, but a concept is a way of telling you what is the interface contract? What should I be sending? In this case, if I'm going to do a sort, I want to make sure that what I pass in is sortable. But again, this is still a runtime check. So what we're doing in concepts now is we're actually creating concepts, our own built-in concepts that are in the standard library that you can use. And so the code you had before is now reduced down here at the bottom to where instead of saying class or type name, you're saying sortable. And it, at compile time, will go out and verify that what you're passing into that is actually something that is sortable. If it's a container that's not sortable, if it doesn't fit the requirements of a container that is sortable, it will actually fail to build for you. And that's a huge break for us, because that means now where we have these problems where we find out that somebody is using the library incorrectly, you're only finding them out at runtime. Now you find them at compile time. These are a few. There's, I don't know, 2 or 3 dozen that are in there. And some of this will change because we're still, C++20 is still in flight. It won't be fully locked down until early next year. Ranges. How many people have ever messed up an iterator? And iterators are a little hard. We did iterators because it was too easy to mess up indexing, and then we found out, well, there's all sorts of ways you can mess up iterators. So here we have a vector, and you're going to sort it. But with ranges now, you don't have to worry about the iterators. Those are now all under the hood. So the second piece of code allows you to just pass in the vector itself, and that will handle, the range itself handles sorting the vector. We're also adding in things like reverse view. So instead of having to do a reverse iterator and you're reverse iterating through looking for the begin, now we're adding a bunch of these. There's a bunch of functions that go to the ranges library that allow you to do that automatically for you. The bottom one is a filter, which is actually very nice. We're wanting to find out if this bit mask is true based on a series of masks. The pipe symbol here in the middle on line 5 gives us a really nice way to express that in the code, and makes it so, again, you're not having to deal with the iterators, you're not having to deal with indexing. How many people think that shared pointer is thread safe? Anybody? How many say it's not thread safe? So 90% of the room didn't say anything. So it is thread safe and it is not thread safe. Shared pointer is thread safe in that the control block, the ref count, is thread safe, which makes sense. But the T, whatever it is, the T that you're passing in is not. And that becomes a problem in that if you are using a shared pointer but you're not actually controlling it with a lock guard or unique lock, you actually don't have any control over it. You can easily have collisions where you have multiple threads operating on the same shared pointer. So this is what it would look like if you were doing it correctly. So in other words, and this actually comes from the paper that we are that's making its way through the committee. Each one of these has to have a lock guard, because every time that you are accessing that shared pointer, you have to control access to it. But with atomic shared pointer, it becomes a lot simpler. You notice up on line 3, it becomes atomic shared pointer instead of just shared pointer. Then all the lock guards go away. All of the the weak compare exchanges are now built in. So I highlighted the lines where it's now actually part of you're actually using the atomic, standard atomic, instead of having to use something different. We deprecated a lot of these other functions that were out there that were causing a lot of confusion. So now you actually have a much simpler way to do it, and as long as if you're doing an atomic shared pointer, you don't have to worry about lock guards, unique lock, anything like that. It's automatically taken care of, which should make your code safer. Volatile. Anybody here use volatile? Hardware engineers? One in the back, yeah. So a few people use volatile. A lot of people have used volatile the way volatile was never supposed to be used, like as a replacement for standard atomic, which volatile does not give you any resource control whatsoever over it. I've seen it used as a qualifier for return types, function parameters. I don't even understand. I'm not sure how someone thought that the last one was going to work, where you're changing the ordering in non-volatile access type. But in we're not getting rid of volatile. What we are is getting rid of a lot of the ways that people have used it incorrectly. Designated initializers. This is something people have wanted for a very long time. C has had this for a long time. It allows you on the bottom, instead of having to do where you do each of these on line 11 and 12, where you do them individually, you can actually do it as a single line now, where you're creating this account, setting the number and the amount. The one thing to remember on this is that ordering counts. By the way C++ lays out its memory, it's different than C, but you have to put it in the same order that it appears up in the definition of the struct. This is also a small thing, but I actually thought it was actually a really good thing. So we've all written code like this, where you have some sort of an enumeration, you suddenly have that enumeration repeated over and over and over again, and not only do you get tired of typing, you forget, oh, I forgot to put that qualifier in there, so you have to go find all the places when the compile breaks. We're now including on line 10 this using enum, which works a lot like using namespace. So it gets rid of a lot of the noise in your code. And I know it seems like a simple thing, but one of the biggest problems that we run into in code, and especially in code reviews, we're trying to slog through somebody else's code, is that there's so much noise in the code that it winds up making it hard to see bugs. So something simple like this winds up giving you a lot of value, even if it doesn't seem like it at the very beginning. Beyond C++20. So contracts was supposed to be in C++20, but there was enough concerns over how it was being implemented. Some of the questions about, do contracts work on, do they work at runtime? Do they work at just at compile time? What happens when a contract is violated? That they were pulled out of C++20 and potentially make it in C++23. Secure clear. Remember the example I told you about? You bring in a key, you decrypt it, you use it, you clear it, you think you've cleared it, but it's not. We're now going to include, we're working on a proposal called secure clear. And secure clear will allow you, what it does is it says, I have this block of memory, I want you to clear it securely. It tells the compiler you cannot optimize this away. And then herbception. So one of the problems that I hear a lot of people talking about is the cost of exceptions is one of the reasons why they don't use it, so there's a runtime cost. I have my own reasons for not really liking exceptions, but runtime cost has never really been the biggest part of it. But we're now creating, it's called herbceptions. It's really, Herbsetter has come up with exceptions which are, which try and deal with a lot of those costs. So those are things, so if you're not using exceptions now because of the runtime costs, this may be something coming up in 23 or 26 that will help alleviate that. I got about 2 minutes. Okay, so Saturday. If any of you are going to be here, I will be doing training Saturday and Sunday. When we think about secure code is really correct code. It's really code that's well tested. It's code that whether it's a user doing something they're not supposed to or it's somebody trying to do something malicious, when your code fails, it fails. When your architecture fails, it fails. It doesn't really matter at that point. It's the consequence that comes after that. But in this case, how do you write highly dependable systems from the architecture on up? What kind of things can you do during code reviews, during testing that will make your code more dependable so that it doesn't fail for whatever reason in the field? So that's this coming Saturday and Sunday. And then this, the first book, in fact, it's based on the series that I've been doing, which is part of it, is coming out in spring or summer of 2020. So look for that. Somebody have any questions with the 54 seconds we have left? Okay, everybody have a great conference.